This is a short video explaining the concept of a simple group. So every group has two obvious normal subgroups, the group itself and the identity element, or the identity group. Now, a group G that has no normal subgroups besides these obvious ones, the group itself and the subgroup consisting of the identity element, is called a simple group. And this does not mean that they're simple to understand. It means they cannot be broken down as a subgroup N, a normal subgroup N, and a quotient group G mod N. So they can't be broken down into simpler groups. And so that's why, in some sense, they're already simple. These groups that don't have a non-obvious normal subgroup. So as an analogy, the simple groups are to all groups as atoms are to molecules. And now chemists have a periodic table of elements. All the molecules are built out of these elements. And so what is the periodic table for groups? Well, it turns out that there's something called the classification of finite simple groups. And I'm going to show it to you in a couple slides. And it's very short in some sense. But its proof is very, very long. I haven't read any of it. It's 10,000 pages, written by hundreds of people over 50 years in many journals. And most mathematicians trust that the mathematicians that work in the theory of finite simple groups have, verified, simplified, or what have you, this result, which I'll say in a few slides. But let's do something simpler, and let's talk about the examples of simple groups. So the group ZP with addition, that's a cyclic group of order P. This is how it's usually denoted, CP, but in this course we've been denoting it with ZP, where P is a prime, is simple. And this is a fairly easy result because ZP is an abelian group, and so every subgroup is normal. So what this result here is saying that the CP is simple is that it has no subgroups besides the obvious ones. And we can use Lagrange's theorem to see why. If ZP had a subgroup, its size would divide P, but the only numbers dividing P are 1 and P, and so the only subgroups of ZP are the subgroup consisting of the identity element and the subgroup consisting of P elements, which is the entire group. Okay, so that was fairly easy to see that ZP is, where P is a prime, is a simple group. It has no normal subgroups besides the obvious ones. What's not so easy is AN, the alternating group on n letters, for n bigger than or equal to 5, is a simple group. And this is not at all obvious. But on the next slide, we're going to check this fact for n equals 5 in Sage. So here's the command for defining the alternating group on 5 letters. So that's what the A is. We've set A to B. And then A.subgroups will list all the subgroups of A. And that's going to be a huge list. And so in order to avoid printing it all out, I just decided to throw that list into the len command, which gives the length of that list. So this alternating group on 5 letters, it's a group of 60 elements, 60, and it turns out to have 59 subgroups. I think it's just a coincidence that 59 is one less than 60. Okay, so, but how many of these are normal? And it turns out that when you do A.normal subgroups, it will return the list of normal subgroups. I asked for the length, and it's only 2. And so that means that A5 is simple. The only normal subgroups are the 2 obvious ones. And now, since this list A.normal subgroups is small, let's print them out. So one element is the list, is the subgroup generated by 3, 4, 5, 1, 2, 3, 4, 5, those 2 cycles. And then the other subgroup is the subgroup generated by the empty cycle, which is the identity element. And so what we're guessing, well, what has to be is that this subgroup, the first one, is the entire group A. And we can check that by accessing this first element by putting a 0 here, because remember Python and in Sage, the numbering of lists starts at 0. So if I type in this command, it will return the first element of my list, which is this list of 2 elements, the one subgroup up here and then the trivial subgroup down here. Okay, and then I ask, is the entire group A equal to the first element? In other words, the subgroup generated by 3, 4, 5, 1, 2, 3, 4, 5, and it returns true. So what this is saying is that this subgroup, the group that's generated by 3, 4, 5, and 1, 2, 3, 4, 5, they generate the entire group. In other words, if you have a subgroup that has these 2 elements in it, then it has to be the entire group. Anyway, so the point is that A5 is simple by just checking in Sage that it has 2 normal subgroups. Now here's the so-called periodic table of the finite simple groups, or the periodic table of groups. So here's this theorem. Every finite simple group is isomorphic to one of the following groups. So a member of one of the 3 infinite classes of such, so the cyclic groups of prime order. So we've seen why those are simple. Then the alternating groups of degree at least 5. So A6, A7, those are also all simple. We've seen in Sage why A5 at least is simple, but we haven't seen a general proof. And then these other groups are more complicated to describe. They're related to matrix groups, at least the groups of Lie type. And I actually confess I don't know what exactly these sporadic groups are, but they're fairly famous in that they come up in things called like the monster, which is a huge group that Robert Grice at Michigan in the 1980s computed by hand, even though it's a huge group. Anyway, so this classification theorem has many applications in many branches of mathematics. Why? It's because sometimes when you're working on a math problem, you can reduce your question to something about finite simple groups, and then due to this classification theorem, you can then check by hand, not by hand, but check each family of such finite simple groups. So there's the cyclic groups, the alternating groups, the groups of Lie type, and so on. And you can try proving something for each of those groups, and that will then prove your result for all finite simple groups. And then maybe because every finite group is made out of or built out of finite simple groups, perhaps you get a result for all groups, or all finite groups at least. Okay, so just a little bit about the history. So Daniel Gorenstein, he announced in 1983 that the finite simple groups had all been classified, but that was a bit premature. And then apparently in 2004, some people, Ashbarger and Smith, published a 1,221 page proof for the missing case. And again, most mathematicians have not read or checked necessarily the proof of this theorem, which is again, started out in 1955 and apparently was just completed in 2004. And they just trust experts in the field like Gorenstein and Ashbarger.